Welcome to our video on the photoelectric effect, one of the key experiments that helped establish the quantum theory of light. The photoelectric effect was a pivotal discovery that challenged classical physics and provided strong evidence for the quantum nature of light. Let's start by understanding the experimental setup used to observe the photoelectric effect. We have a vacuum tube with two metal plates, a cathode and an anode. The cathode is the plate that will emit electrons when light shines on it. A battery is connected to create a potential difference between the plates, and an ammeter measures any current flow in the circuit. Now, let's see what happens when we shine light on the cathode. When light with sufficient energy hits the metal surface, it can cause electrons to be ejected from the metal. These ejected electrons are called photoelectrons. They travel across the vacuum tube to the anode, creating a measurable current. Scientists observed several interesting phenomena in this experiment. First, no electrons were emitted if the frequency of the light was below a certain threshold, regardless of the light's intensity. Second, increasing the light's intensity increased the number of photoelectrons, but not their energy. Third, increasing the light's frequency increased the maximum energy of the ejected electrons. These observations couldn't be explained by classical physics, which treated light as a wave. In 1905, Albert Einstein proposed a revolutionary explanation. Light consists of discrete packets of energy called photons. Each photon carries an energy proportional to the frequency of the light, given by E equals h times f, where h is Planck's constant. This led Einstein to formulate the photoelectric equation. The maximum kinetic energy of ejected electrons equals the energy of the incoming photon minus the work function of the metal. Mathematically, this is expressed as Kmax equals hf minus phi, where phi is the work function, the minimum energy needed to remove an electron from the metal surface. Let's visualize how this equation explains the observations. First, if the photon energy hf is less than the work function phi, no electrons will be ejected since Kmax would be negative. Second, increasing light intensity means more photons, which gives more electrons, but each photon still has the same energy. Third, higher frequency light means more energetic photons, resulting in electrons with higher kinetic energy. The photoelectric equation was experimentally verified by Robert Millikan in 1916, who determined the value of Planck's constant with high precision, confirming Einstein's theory. This discovery was revolutionary, as it established that light has both wave-like and particle-like properties, a concept known as wave-particle duality. For his explanation of the photoelectric effect, Einstein was awarded the Nobel Prize in Physics in 1921. To summarize, the photoelectric effect demonstrates that light consists of discrete energy packets called photons. The energy of each photon is given by E equals hf, and the maximum kinetic energy of ejected electrons is Kmax equals hf minus phi. This discovery has led to numerous practical applications, from solar cells and digital cameras to night vision technology and electron microscopes. The photoelectric effect marks one of the key turning points in the history of physics, helping to usher in the quantum revolution. Thank you for watching this video on the photoelectric effect. I hope you now have a better understanding of this important quantum phenomenon and its equation.